Refraction is what happens when a wave transfers between media at an angle. Imagine you are riding a car through a puddle. You're going to be taking a moving object from one medium to another. You know from experience that water slows objects down, so you're expecting your vehicle to slow down. As it does, the question becomes, what happens if you hit the puddle at an angle? Unlike previously, we are now going to treat a wave as a wavefront rather than a point. The wave now has a profile rather than a spearhead. Different parts of this wavefront interact with different parts of the environment depending on where they are. Our wavefront approaches our media interface. Our car approaches our puddle. We hit the interface at 90 degrees to it. Our car strikes the puddle head on. The entire wavefront slows down at the same time. The whole car slows down. Now we'll do that again, but at an angle. The wavefront approaches the interface, and the leading edge goes over the interface. The car hits the puddle, and only one wheel goes in first. The section of the wavefront is slowed down compared to the rest of the wavefront. The wheel is slowed down, but the rest of the wheels maintain their higher speed. The wavefront not in the new media catch up with the slowed down part of the wavefront and cause a change in direction of the whole wavefront. The car turns towards the puddle. The rest of the wavefront enters the new media and continue on in a straight line, different to that previously, but at a decreased angle to the interface. The car goes straight, but pointing into the puddle more. The wavefront reaches the other side of the medium. The car gets to the other side of the puddle. One section of the wavefront enters the faster medium and speeds up. One wheel of the car leaves the puddle and speeds up. The leading edge of the wavefront speeds ahead of the rest of the wavefront and causes the wavefront to change direction away from the interface. The leading wheel makes the car turn away from the puddle. The whole wavefront enters the new media and has the same higher speed. It continues on in a new straight line direction. The other wheel leaves the puddle and travels at the same speed as the first wheel. The car drives off at a new direction away from the puddle. All of this is summarised in a property called the refractive index. It tells you how the change from one medium to another affects the speed of the waves travelling through it. The refractive index of a boundary is equal to the speed of the wave before it enters the medium, divided by the speed of the wave after it leaves the medium. For light, we can simplify this still further. If we assume that light waves enter a material from a vacuum, then we know the initial speed of the wave, and that this value does not change, and no other value can be higher than it. It is the speed of light in a vacuum, 3 by 10 to the 8 meters per second. A material will always slow down a light wave that has come from a vacuum, so we can give this material a value called the refractive index. If an interchange has a refractive index, it is the value between the two materials, not the material itself. If a material itself is given a refractive index, it is because we are comparing it to a vacuum. Because light cannot travel faster in a material than in a vacuum, the refractive index of a material can never be less than or equal to 1. These refractive indices of material can be used to explain more about the motion of waves through materials at a plane surface.